Yeah. So, I am Arun Kumar, scientist from CWPRS, and good morning to all. Today our lecture, first lecture is hydraulic model study for river engineering. This is the course actually, design of hydraulic models for rivers. Means I think how many of you have seen the model, physical model till now? Nobody has seen. Okay. Good. So you might have seen here Nihari. Okay, afternoon we will be having a visit. You can understand better after giving the lectures. No? So there is one little modification today's lecture, that analysis of bank line changes, it will be shifted tomorrow. And tomorrow's development of 1D model including hydraulic structure which is being presented by Mrs. Josna will be done today itself. So continuously there will be introduction plus demo. So continuously she can take afterwards. So today one lecture only, and tomorrow we will shift this analysis of bank line changes to tomorrow's. That is only one change. So in physical model actually care is required to be taken at the design stage itself, because in the prototype when you construct a dam, barrage or any structures, it requires lot of money, means 1,000 crores or more than that. So if the design goes wrong, hydraulical design goes wrong in the initial stage itself, then after construction of any structure it is very difficult to correct the things, because it is very difficult after post construction scenario, because you have to change the alignment, all those things is very difficult. So care should be taken in the design stage itself. That's why these physical models are one of the important tool. I don't say it exactly predict the same as a prototype, but you will get some idea what will be the hydraulics involved in it and what is the corrective measures to be taken in the initial design stage itself, like energy dissipation, adequacy of energy dissipation. All these things can be studied in the model before implementing at the site. So before the work effects anticipated to be achieved and the negative effects are minimal as much as possible. So there may be some negative effects in the design stage itself, that after modeling you can rectify those small issues, those negative issues, and you can have a good design and long-standing design of the prototype. So advantage of scaling down, as I told you earlier, it requires 10,000 crores or 1,000 to 10,000 crores in big projects. So in such cases, for model construction, it may be 0.01% of that cost. So that means you can have a model with a lower cost, instead of having some risk analysis like constructing a faulty design at the site. Instead of that, you can have a model with a smaller amount of 0.1% of the total cost as a physical model. That is one advantage of scaling down. Then the process takes place in the models much quicker than the prototype. Suppose if you want to have some river training works like construction of spurs in the physical model. So alignment, its orientation, everything is required to be taken up carefully at the site. So in the model, it is a half day's work. You put one small barrier like sort of thing like spurs, and we can see the performance of that spur on the model in a quicker direction. That's why the process takes very small, means quicker than the prototype. Prototype requires, you cannot play with the prototype value. So these things can be done in the model. So there are different types of hydraulic models. One is geometrical similar, means all the horizontal as well as vertical, both are compressed down to a single scale. Means if our length is 6 feet and width is about 1 feet, we will be reducing it to divided by 10, means proportionately you are going down. That is called geometrical similar. So then next one is distorted. Now anybody can tell me whether Why the river models are generally distorted? Do you have any answer, anybody? Why is distorted generally?
Because it represents physical, the real, since it's a prototype or a model. So
Yes, you are right, but I can go for geometrical similar.
Longitudinal dimension is much bigger than the other dimension.
Correct. Means river is flowing at a kilometer wise distance. Say 10 kilometer river, you are modeling 10 kilometer. Width, what is the width? Say 3 kilometer. Okay, space wise you are okay with that. But what is the depth? Maximum depth will be 10 meter or something. So this ratio is very, very small. If you make a geometrical similar, what happens? Your depth becomes 1 centimeter or below that also. Then what, whether it replicates the prototype? Because prototype lot of turbulence are there. That is not generated here in the model. That's why we distort the things. Means horizontal scale is lesser. Vertical scale is lesser than the horizontal scale. Say 500 is the horizontal, vertical scale will be 70, example. So then you will get the sufficient depth. When depth is small, then what happens? Laminar flow will be there. So your Reynolds number will not replicate as prototype, because you can see in the prototype during flood lot of turbulences are there. So that is not being represented if you make a geometrical similar for a longer reach. So then we have to go for distorted. So then I will explain you the factors which are affecting these distortion, means numbers, Proud number and Reynolds, I will explain later. Then vertically exaggerated model is fixed bed and mobile bed. Fixed bed means you are going to plaster the things. There is no movement of sediment. So the bed, whatever the river cross sections are there, that is being plastered. So bed movement is not. That is called fixed bed model. And mobile bed means you put sediment. These movements will be there. That is called mobile bed models. And what is 2D model? Suppose if you want to study a single barrage width or a single pier of a bridge, want to study that thing, you need not require a big large model. You require a small flume. You might have seen in our college days that a flume studies 1.5 meter to 1 meter, like that. Width is only that much. And you are placing a pier or whatever base of this one, barrage. Then you are studying a single point there. Not a holistic, means throughout the bridge you are not putting a single pier. What will be the scour pattern? What is the energy dissipation or elements of single bay of a barrage? All these things can be studied in 2D model. That is called 2D flume model. Now here you can see a typical geometrical similar rigid bed model. Means the bed is plastered here in this case. So there is no movement of sediment, and whereas here it is distorted plus mobile bed model. This is a bridge, actually a bridge model of Gumuda in Vamsadhara river. You can see the bed is mobile. So when you take water, there will be movement of bed material. So the main criteria of this one is the adequate reactive force into satisfactory bed movement. This is in case of mobile bed model. For rigid bed model, this will not have much effect because you are going to plaster it with the smooth. Ultimately what happens, Manning's and roughness coefficient is to be represented properly in the model, equal to prototype. That I will come in the later stage. So the adequate tractive force, what is tractive force? Tau, critical. See, exert the movement of the bed material. What is the force required to exert that movement of bed material? That is called a tractive force. That is adequately done in the physical movable bed matter. Then proper discharge scale. So discharge scale should be there. So I will tell you later regarding the discharge, what is the discharge scale. Then sufficiently high Reynolds number, that what I told that. If you make a geometrical similar for a longer reach, your depth will be very, very small. So Reynolds number will come into effect there. So then Reynolds number should be there to create a turbulence as just like a prototype. Then other practical considerations are length scale to be appropriate to the available space. Then actual model depth to be neither too small nor too big. When it is too small, as I told you, there will be laminar flow, no turbulence. But when high this one depth is there, then your bed movement may not be there. So or erosion of bed material may be there. Am I audible now? Okay. Then the different scale designs worked out are to be finally compared and the best of are selected. That is how actually you generally take the table actually. Here you make a table here. Here scale 1:500 and 1:70, then 1:400, 1:60. Likewise, you go different tables. Then you get the space, means L into B tray. What will be the, suppose it 10 kilometer, 10 divided by kilometer divided by 500, your scale. What will be this meter, so much meter in the model, and vertical scale. Vertical scale, ultimately what happens as a thumb rule in the model, three things are to be kept in mind. One is space. Space is equal to L into B. If you have a model tray of that one, you can adopt this space. This is to be kept in mind. Second thing is discharge. So discharge is LD root D. I will come in the later stage, explain in the later stage. This Q should be available to our model limitation. So whatever infrastructure we are having, whether we can get that discharge in the model or not, that is to also be kept in mind. Third one is head. Head means you have some upstream level, downstream level of the prototype. So when you convert it to the model, it should not happen that your downstream level of the model is lower than the outlet channel. What happens? Outlet channel is more, and this one is backwater will be there. So model will not be there. So this head to be. So it is ultimately what happens. The model is in a Freudian model. Gravitational force is predominant. So you make a table and make all these things: space, discharge, then tractive force, then sediment particles, water. All these things you are. So when at some stage you will get some criteria of this one. Space is available, discharge is available, head is available, and the fourth one is sediment, this one, tractive force. What is the sediment availability? That if all the things are done, then you have to select the scale after making a table. Not a single go you can decide that this is the model scale. That is important. So that's what I was meant to say here. The different scale designs worked out are finally compared, and the best is suitable is as per our infrastructure. You have to decide based upon that. See, there are different scales of model in CWPRS. One Kosi River, 570, Ganga. See, generally it is in this ratio. You can see the distortion ratio here. It varies from 3.8 to 7.1. So 3 to 7 is the best distortion. So you will get all the criteria fulfilled in this one. So of course there are different other numbers like Mach number, Euler numbers, and all these numbers are not predominant. It is neglected. I will explain in the next slide. See, principle of similitude. One is geometrically similar. So length scale ratio is equal to same thing. Then kinematic viscosity means what? Velocity, all those things or acceleration due to gravity, all acceleration, the flow velocity, all those things is kinematic similarity. That prototype and model should be satisfied. That is the one principal similarity. Then dynamic force acting on this one. So what are the different forces? These are bottom one, pressure force, gravitational force, viscous force, surface tension force, and inertia force. So it is basically everything is related to inertia force. So in Euler's model, that pressure force is predominant. Pressure force by inertial force should be equal to 1. This is Euler's number. This is not much important in the model, only comes when the depth of the flow is very, this one means pressure flow is this one. Conduits and all those things modeling, this is important. Then Froude's, this is the main criteria. Whatever the hydraulic model, physical model, is the Froude's model generally say. Freudian similarity. So Froude's numbers means what? Gravitational force by viscous force, inertial force. That should be equal to 1. So this is the number, V square by root GD. V square by GD. or is this Froude number of prototype and Froude number of model should be, this criteria should be followed. That's why this is the important number, dimensionless number of hydraulic modeling. Third one is Reynolds model, viscous force. That comes what I told you earlier, turbulence is not been created. So how to create a turbulence, then this number comes into picture. So the values I will explain you later. So flow pattern now. So major flow on the flow is inertial force and gravity force. Now here how you can, you have a VER is equal to, so velocity ratio is equal to root of y. Root of y means depth scale, y means depth. How it is related, because FR is equal to V by root GD, right? Then if FR is equal to 1, this prototype and model, it should be equal to 1 as per similitude. So V by root GY or GD is equal to 1. So what is G? Acceleration due to gravity. So this is open channel hydraulics, prototype is open channel. So gravitation there and here both are same. So it gets nullifies. So V is equal to root of D. So whatever the scale you get in the velocity get in the model to be multiplied by root of the depth scale, you get the prototype velocity. That's why this is V is equal to root of y. So flow pattern will be similar if prototype number in the model and prototype in the model and prototype is same. Now coming, so check this equation Manning. These two equations are main equations used for deriving the model scales. So here you can see V is equal to 1 by n. This is Manning's formula. You know 1 by n r to the power of 2 by 3 and s to the power of half. So r is a by p, hydraulic radius. So when 1 by n is equal to r of 2 by 3 into y by x, means this distance by the change in depth, that is slope. Slope you know, y by x to the power of 1 by 2. So for wide rivers like alluvial rivers, wide rivers, a by p is r is equal to nearly equal to the depth. You can you know this is well known fact, in your textbook also it is written like that. So then what happens when r is equal to y, VR and VR is equal to root of y, which I told you in the previous slide. V is equal to root of, then you substitute all these values. So nm by np is equal to yr to the power of 1 by 6 into y to the power root of 1. For undistorted model, y by x is equal to 1, means undistorted, geometrically similar, both the things are same, right? Everything you are scaling down. So y by x is equal to 1. Then leads to n to the n is equal to nr is equal to yr to the power of 1 by 6. Means your Mannington, whatever the Mannington of the prototype, you will need to get us the NP getting material is difficult. So the materials which you get in the model is very small. You see 1 by 6, rise to the power 1 by 6, you have to divide it. So when you divide it, your material size, whatever you require is very small. Micro this one means it is very small. You may not get that one. The least possible what you get is coal dust or sawdust, all those sawdust, not walnut powder. These things have to be used. So getting those things are very difficult. You require a large quantity. So materials you are getting is very difficult in this phenomena. So in the distorted model, nr is equal to nm by np is equal to y to the power of 1 by 6. This is the formula I have derived last. So now when it is greater than 1, n is dependent on dr. Dr means d50 of the material. This is the formula k into d to the power of 1 by 6. This is called Stickler's formula. This is generally used for your this one modeling scale of Mannington calculations. So therefore, when you substitute these values, nm is equal to np, because your prototype of n value means roughness, when it should be equal to model, then what happens? This gets 1. So 1 is equal to yr to the power of y by x r to the power of 1 by 2. If you simplify this one thing, then you will get xr to the power is equal to y to the power of 4 by 3. If you simplify all these things and substituting all the yr and all those things, you will get this xr is equal to y to the power of 4 by 3. This gives the model scale. So when for example if you have 100 this one, that's y, what should be the y, you can calculate it based upon these equations. So fixing the models as per Freudian law, VR is equal to Vp by, this is root of y, I told you the last. So time scale will be x by root of y. This is the time scale. So in physical model, because of this factor, you cannot run an unsteady model, discharge in the physical model, because your time scale will be very, very small. If you have a 1 hour, you have to make it in a 1 minute or something like that. So controlling the water or the discharge or the downstream condition, whatever the hydraulic conditions are there, you cannot make it in the model in a shorter period. We require some time. So unsteady model cannot be run in the physical model because of this time scale. Then Manning's these equations. Here you can see if 100 is the y, then x will be, as per this equation, you will get this. So this is the distortion will be nearly 5. So this is the thumb rule. So when you want to construct a model, if you have decided the horizontal scale, your vertical scale can be based upon this one. This gives the nm of the prototype and model is almost equal to same. Means whatever the D50 material of your prototype and D50 material of your model will almost be same. Ultimately, whatever tractive force is the main thing, which I will tell you later. This is the tractive force, incipient motion of model, this particle, sediment part. What is incipient motion? There are 3 type of movements are there. One is rolling, second is hopping, third is saltation. Rolling means whatever the bed material, this rolls down. It will not jump, and the hopping means it jumps and goes to the downstream. Jumps and goes to this phenomena. The third one is saltation, means this one, muddy water or something. It is in suspension, all the particles. That actually we are not reproducing in the physical model because of the constraints. Because sometimes we will put this sediment injection studies or something like that. That we will mix the things and we will input that in the model. But as of now, the clear water will be fed into the model. So this saltation will be there, not there. But the 2 criteria, hopping and rolling, that should be visible in your physical model. Then you will say that my physical model is behaving just like the prototype. You can see in the model also. Afternoon when you go and see if you see the model, you see bottom materials get little bit. It is not that it is washing away completely, but it is stationary. There should be movement. Then it is called incipient motion. Though force exerted to move the sediment, that is called inertial force, tractive force, which is required. That has to be kept in mind. So here you can see this is called a Shields curve. So whatever the curve above this one, this is under motion. So below that one, this is stationary. So you have to select the bed material so that the tractive force will be matching with the tractive force of the prototype is matching with the tractive force of the model for the bed material. So this is the shear velocity, that GYS root of G. This is based upon Chedji's equation. So for particle of Reynolds number less than 5 influenced by laminar supplier. So what I was meant to say, that when the depth is low, it will be, the Reynolds number will be below 5 there. So it is not a criteria. So particles 200 to 500, then it is transition zone. Means your particle may be stationary, sometimes it may move, sometimes no. It is also little bit complicated. But when you have a sufficient Reynolds number above 200, it is completely turbulent, but at the same time you have to see that all the bed materials are moving in a proper way. Not that if you take a water, all the things are going downstream and you are collecting again and coming upstream. It should not be. So in a period of time, gradually it should move. That is the tractive force required to exert the movement of sediment, and along with the turbulence required in the prototype. So the constant, this is the parameter is 0.04 is the approximate value of critical shear stress parameter. So beyond Reynolds number of 5. So it is 0.04. Here you can see this 0.04, whatever the material, this will be there actually for the general, this one, the Reynolds number is more than 5. So then model limitations. So I told you earlier that everything is being given by the physical model. It is not like that. Physical model is a tool to understand the flow behavior, flow phenomena actually observing on the prototype. So it doesn't mean that whatever the prototype values are there, your model will give the same thing. There are some limitations. Then river bed forms are the result of the natural flowed hydrographs over the period. It would be very difficult to reproduce the actual hydrograph in the model. That's what, because of the time scale I told you, hydrograph cannot be run, because in the prototype there is a lot of hydrographs comes in every year. It comes, high peaks, and then lower limb will be there, then it lowers down. So that phenomena cannot be run in one. That is the limitation first. The slope of scour holes. So scour holes which we see in the model and prototype will be not be exactly same. Because why? Because it distorted. So that's what that scale effects will come. There will be not much actual scour pattern observed at the prototype cannot be replicated in the model. It is qualitative only. That is second one. Then wear coefficient exerted due to crest high increase. So in a small structure, the CD value or the coefficient, whatever the wear coefficient or CD value, generally we say coefficient of discharge, then that might not be properly produced in the physical model. So now I come to our CWPRS. So this is the area of CWPRS. You can see a lot of models. These are all models. So this brown line, this grey line, this is a circulation system. So from Kadakosla Dam we take water, lower head tank, we pump it to the higher head tank and circulate it to these pumps. So these canals are throughout the periphery. There are three systems. One is 120 cusecs of discharge capacity, 100 and 60. So three systems are there. So in each system we have different pump house. But the main thing is that when we take once the discharge, it goes and comes back to again to the pump house under gravity only. So we don't have to pump anywhere else. So it goes and goes to the pump house, and at pump house again it pumps down to the canal system, and it is like it goes on. So in the model also we should take care that what I told, space, discharge and head. So then head will come into picture. So we have to design the model such that the top portion, model and bottom portion, it should have some differences in each step. So then only you get the free flow. Otherwise somewhere downstream your canal will be higher, your model will be lower. As I told earlier, backwater will be there. So that should not always be there. So these things are there, and in model also we have to design in proper way, that considering all these arrangements, circulatory systems. So these are the blue lines are circulator, 100 cusecs, 40 cusecs, 120 cusecs, and 60 is also there. 40 is in the Mumbai model area, that too for particularly meant for Mumbai because it is a big model. So in 60 cusecs is there in the other side of this one. Then 100 and 120 is main circulatory systems. So there are 17 such octagonal chambers. These are distributaries. So when leading canal comes, then it comes to the octagonal chamber. So here there are 6 models. This is model 1, model 2. These are distributors. You can take water to any models nearby. So nearby we have such octagonal chambers, and this is the bypass channel. Means when the excess water is coming from the inlet, we will bypass it to the outlet, and it will go to the pump house again. So in the between, all these goes to the different models. This is the octagonal chamber. Here this is the inlet, this is inlet, then this will be the outlet, and these are all models. Here this goes to one flume, this goes to another physical model. So when the model is not there, means it is abandoned, then we will close it, or we will make it take a barrier in that, so that the discharge will not pass through that canal. So this is how the system is there. So this is what I was meant to say earlier, that head means you can see the octagonal chamber. So the distance between the difference between the head of this one to the inlet chamber, that minimum 15 centimeter gap should be there. Then it will fall as a free flow here. From inlet chamber here to the inlet of the model, there should also be 15 centimeter, means it again drops down. Then when the model comes and this is the outlet channel, there also be 10 to 15 centimeters distance should be there, means from the higher. This is what I meant to say, the head. This is the longitudinal profile of the model from observation, this one octagonal chamber or your measuring system, from there itself to the inlet chamber 15 centimeter, then to the model 15 centimeter, then exit also 15 centimeter. In between there may be variation, like bed variation will be there, depend. But ultimately the end and starting point of your this one model should have a difference, that is called head. So head space you get, because space is length by breadth, you will get a lot of space. Head you get. Then comes to discharge. What is discharge? Q is equal to A into V, that is general formula, right? So A is equal to L into B. Okay, you know L into B. Then what is V? I told you earlier. Where V is equal to root of D, right? So L into D means length scale into depth scale into root of D, LD root D. This is the quantity. Suppose you have 100, geometrical similar say 100 into 100 into root of 100 means what will be this one? 1 lakh, I think. 1 lakh it will come near about. So this is the quantity which you have to divide it on the prototype value. Suppose your 10,000 cusecs is there, your Qmax is there, discharge. Divided by this quantity, you will get the model discharge. This is how Q into A into V. In that dimensional analysis, you will get that quantity, LD root D, that has to be divided by the prototype. You will get a model. So if you get a model, our model one pump has a capacity of 20 cusecs. So we have two pumps, 20. After loss of every loss, because it is a old system, canal also there will be a lot of seepages and pump capacity may also be lower. So when you get the ultimate discharge, you may not get 20 cusecs in a single pump. You may get 10 or 7 cusecs. So that 7 cusecs you keep it in mind and you design the scale. Whether the scale, so then it comes to space is okay. You will don't have a problem in the space as far as you are, even in Nihari also, you have got a lot of space. Space is not a constraint. Discharge and head. These two things has to be repeatedly, iteratively you have to make a table like that, and at one instant you get all the criteria satisfied. Space you get, discharge you get, it is sufficient, then head also you get. Then you have to decide. This is for geometrical similar. The fourth criteria when it comes, only during the mobile bed model. Tractive force. What is the tractive force required to move the exact the movement of the sediment? That is in the this one, that is tau in tau, that tractive force is equal to gamma into Rs. Gamma is specific gravity of water, R is equal to A by P, and S is the bed slope. So you get the tractive force, that critical tractive force which is required to be exerted at the moment of sediment, that you have to be equal to the prototype value. That's why how you define the different scales. So this is the layout of model. So what is the datum? Datum is not the datum of the prototype. It is a temporary datum you fix in the model. So you have a upstream model boundary. There you have a section, cross section. Suppose your cross section, the top level is 100, floodplain, not deep channel. 100 is your top level. What you should, and downstream most you take a section. There what you may get it 95 top level. So what should be the datum? We generally put 5 meter extra. So 100 is the, I told you, maximum at the upstream, and 95 is downstream, maximum top of the this one. Then you take 5 meter extra. So 105 is your datum. That is what we say datum. We have to fix it based upon your measuring instruments like standing wave flume or Reebok wear, discharge measuring system. What I told you earlier, so discharge measuring system should be 10 to 15 centimeter above the inlet of the model. So you know the top of the measuring system. So from there you make take 10 centimeter below, and fix the point and allot it as 105. That is called datum. That throughout the model you have to construct it. It will be better because the datum will be same. So putting cross section will be easier if you put a common datum on all the sides. So all the this one I will show you in the next slide. So then what happens? Your model tray will be there, preparation, excavation will be there, preliminary excavations, all these things, because you have to build a tray. So while building the tray, you have to build whatever your deepest channel is there. From that, it is minimum 2 feet is best as far as possible. You go 2 feet below the deepest channel of the river in your model, 2 feet below. So in bottom layer, you put a concrete, so that there should be no losses of water percolating into the ground. So you make a tray full throughout the model, a 6 inch or 4 inch concrete. Then over which 1 feet murum, good quality murum. Why murum? Because you have to plug a this one iron rod or this one bamboo sticks there. So it will again hill rise. Actually, it will go on bending or something like that. So for firm grip, you should put a murum, over which you should put this one either sand, or if you in case of mobile bed model, or you can plaster in case of rigid bed model. This is how done. So then you get the prototype value. See, X is the chainage and Y is the RLs, means bed RLs. So how you suppose this is 160 and vertical is 40, and I told you datum I have put 105. Then how this will be? This will be X will be directly divided by 160 horizontal scale, because it is a horizontal dimension. So you get this one. This is in a meter. So multiply it into 100. You get centimeter, because generally we opt to mm or centimeter for precision in the model. Then the level here. So in 96 means you have 105 is your datum, right? 105 minus 96.9. This is the bed. So what will be the difference? Divided by your vertical scale is 40 into 100, you will get to this centimeter, 0.2 meter. Means 0.2 meter is below the datum line. Right? Could you understand this one? See, this is the cross section actually, and this is the datum. This is 105, right? As per mine. So you put a thread here, nylon thread. This is line is 105. So here what is I told you 20 centimeter is first, this one is 20 centimeter, means from here it is 20 centimeter. How this has come? Because suppose 96 is your bed level and 105 is datum. This is 105, this is 96. So this one 9 divided by 40. 40 is your vertical scale. Multiply by 100 is equal to 20 centimeters, so 0.2 meter or 20 centimeter, right? So from here it should be the peg, which is you driving the peg here, it should, the top level should be 20 centimeter below this one. So you have a depth rod which is demarcated from 0 from the bottom and 1 meter in the top. So you put a depth rod here and you drive this plug such that your this one will come to 20 centimeter. Till then you have to put it. So you get this one. Likewise you get all the plugs. So you will have a profile. Then join that profile, that I will show in the next slide. This is how we done converted into the model scale. So this is how done. You can see this thread, yellow, green thread is there, no? This is datum thread, means 105. And this man is putting here this one. This is the peg. See, you can see bamboo stick. You see this one. So till 20 centimeter. In this case, if you put this one, if we get 10, then he stops here. If it is less, then he drives. Then you get one such type of points on the cross section. Likewise, everything you have to get. Lengthwise, you know this one, no? Lengthwise, total 26 centimeter. So and this is the level. So in 48 centimeter in the model, you get 18.3 centimeter down. Like that you get a profile here. See another picture. You continuously he is driving this one for different scales. Here is the this one. This is a chain edge and this is the bed level. Then next is generally in our Maharashtrian this one you generally say Havari. Havari means molding, just like a molding. So you have to make a strip. You have a cross section. One cross section is over next cross section like that. In each cross section you have to make a strip. By making this one, you get the profile and join it to the consequent cross sections. You get the deep channel. Where is the deep channel? Then you have to see your index plan. You will come to know what will be the channel and what will be the groundwork. So these are all things. Then after construction of model, one thing is that you have to validate it with the prototype. How do you do the validation? Prototype value. And there are two boundary conditions. One is inflow. Inflow is the discharge which is passing. That I told you how to convert it. So you put a discharge. The particular discharge, there should be a gauging station downstream. You have to control for that one. So you have to ask for the project to give the gauge discharge curve at a area of interest. So you maintain that one the downstream and you will get the water levels. So that water level should be checked in the prototype value. One or two locations they will be having water level for a particular discharge. If those matches, then your model is calibrated. Then after calibration, you can test all other this one like spurs. You can test spurs, porcupines also. In these days we are testing porcupines also in the model. So there is one this flow measuring angle also. It is generally not available in all models. Actually, we have developed it in near Pune in earlier days. That we put a thread on the bottom portion where the man has a finger. No, here we will put one thread, and we will see align it to the flow. When the flow is there, that line should be in a straight line. So then there is a demarcation in the top that what is the angle. So we will get the angle. So just like you have seen in a 2D model mathematically, you see a velocity vector. In the same manner we can have a velocity vector drawn in the model also, physical model also with this one. You know the velocity, take the velocity from the current meter in the model, you know the velocity. So you can make a vector scale also with the angle with this type. Then this is the current meter. So right side there will be this one means current meter. What will be the velocity? It will directly give. So then gauges. In these days we replace the manual gauges with the electronic gauges here. So this is also a gauge. So why is gauge inverted here? Can you tell me? Because in the prototype, your gauge post, most of you are from field. Gauge post is how it is from the bottom to top, and its width will be about certain width will be there. So if you put the model in likewise, what happens when the flow comes? It will be obstruction there, because model is very small. Means the scale is very small compared to prototype. So what a small change in this one will get a wrong water level. That's why we put it as an inverted gauge. With respect to datum, we measure the things. This is in case of rigid bed model. So strips are being put, then we plaster the strips like this one. This is rigid bed. So SW, standing waveform. This is a discharge measuring instrument. This is the old system. Nowadays we have replaced it with this one, thin plate wear or Reebok wear. For V-notch also you can see, but V-notch will get a lesser discharge, and Reebok wear you get the accurate discharge. Only thing is that for Reebok wear you have to make a hole on the downstream to remove the negative pressure created under the nappe. That is the main thing. But here it is not like that. But the accuracy is more in Reebok wear or thin plate wear compared to standing one. This is the old system. So I will just put one, another 10 minutes I will take, because 11. So Katargada weir is in Vamsadhar river, you can see here. So barrage was, Naradi barrage was proposed. So there is a problem with the Orissa and Andhra Pradesh. So backwater effect studies was required to be done. That is one thing, but later there was a side weir proposal here in side weir. You know what is side weir? The flow is going there. A weir is cross section along the flow. Weir constructed. It is called side weir. So this is spatially varied flow. Discharge will be passing, drawing from the main river to the side weir. So this is the side weir. Likewise, 300 meter was there. Then this is the profile canal. After the side where it goes to the canal. So the scope of the model was to give the discharge for different discharges like 150, 200, 400 in the river. What will be the discharge passing through the side weir? This was required to batch assess because nowadays what till now there is an empirical formula available in this one calculation of side weir. There is no, and it is also for prismatic channels, not for river. So that was the main criteria here in this one. So we have to assess what is the discharge passing through the side weir. So gauge discharge curve. This is the inlet flow and this is outlet. This is one inlet. Discharge was passing, and this is the control gauge, the outlet. Particular discharge, what will be the, so this is the water level at Katragada, means near this one. So this is the model. How you can see, this is the embankment, and here this is the under existing condition. We have run the model, and this is the area of side. This is the condition with the existing condition without side weir. Side weir was not considered, but this is the location of the side. So we observed these things, all the hydraulic parameter here for 200 Qmax and for 400 Qmax. These are all. Then for existing condition for 8,000. So it was almost submerged. So here in 1699, this is the maximum discharge. Everything is under submergence, side weir, everything. So then we constructed this side weir. This is the crest of the weir. This is escape channel, means excess what are the sediment is collected in the basin. This is being removed to this one and passed again to the river, main river. And this is head regulator, canal. So this is construction. You can see the construction of side weir. So this is an existing condition. This you can see little bit of water was passing, not negligible passing of this. Then for 200 years, little more discharge has passed here. So these are all floats actually. So here in 400, so more discharge has passed here. Then 8,000, of course, most of the things has passed, and it here same condition. Under existing and floor, everything is submerged. This is the very peak discharge which is observed till now in Vamsadhara river. So you can assess what is the discharge passed. For 400 discharge in the prototype, you can pass a 145 discharge in the side weir. This is how we can arrive at this one. So the other things are there also. So what are the hydraulic parameter like velocity, water levels at different points. So this is the advantage of physical model. You can have a observation at point velocity wherever you require. So under the low flow stages, flow pattern with and without side weir were similar for a length of 300 meters. These are the conclusions. Of course, I don't go much into this one. So then activation of channel in Kosi barrage, mobile bed. So there was a pilot channel proposal here in the Kosi. This is the Kosi barrage upstream. So a lot of spurs are there. So there is a problem in between 27.88 and 24.78. This is in between there is a problem in the river. So we have done a model studies. This is river Kosi. The model is having 570 scale. If you visit the CWPRS, you can see that model. So these are all. So this is the upstream point, and this is the dry model, and this is the proposal, pilot channel. That was the proposal of the project authorities. That what will be the performance like that. So sediment, all those things we have injected. This is injection of sediments. We put a sediment in a certain quantity that is sediment injection rate. It is qualitative only, not as per the actual this one. For a particular discharge, what will be the sediment rate, that we will just inject it into the model to see what are the covering or deposition pattern in the model qualitatively. So this is the existing condition. Now you can see after existing condition, you see the scour here near the scour holes when you stop the model. So this is the pilot channel. In the maximum this one everything. So there is no much difference in the velocity reduction after providing a pilot channel here. This is what we saw in the model. So then what we told them is that you put a resistance to the main river by providing porcupines. Porcupines, you know, I think tomorrow he will explain. You also know that, I know from field everybody knows. So what we done is that we put a porcupines here and we asked to enlarge the mouth of this one right channel, so that the discharge will be lesser on the left bank. So we asked them to make this dotted line, bell mouth shape like here, with porcupines here in this area. So you can see the reduction in velocity on the eastern, means left side, you can see the reduction, green one, lot of reduction was there, and the increase in velocity and discharge on the right side. This is how you can play with the model, how you can train the model, or you can make a pilot channel or in alterations in the model. Whether it is practically possible, that also be looked into, but you can play with the model because you don't have much required much time to alter these things. So here you can see this is the case, and the velocity is lesser on the left bank, and maximum velocity was flowing in this one. It's another view of 14,000 discharge, means maximum discharge. So you can see post flood barrage. This was a small level, and after our widening here, you get more discharge here, and there was a little this one, means problem in this one. Of course, this is the post flood, those two images are post flood, but different discharge dates are there. So that's why what we told, that pilot channel is not going to work. This is because they are investing lot of money in dredging the pilot channel. If it doesn't work, then lot of waste of money. So we told that you just make a arrangement near the mouth of the channel on the right side and put some resistance on the main channel, so that the discharge will be passed on the right side rather than the left channel. So you can do flume studies. This is what I told you. This is a Gaigat jetty in Ganga. This is jetty. So what will be the effect of these? These two are the piers of the bridge, and this is jetty. What will be the effect of scour of this pier on the jetty pier? This we can study in the 2D model. You need not have a bigger model. So 2D means this is 1.52 meter width model. So you can see the scour pattern here. What is the scour pattern? Then this is the prototype. After our model studies, they have constructed. So it is working nicely now. Till now it is there. So then this is one thing, that structures, when you get a distorted model, your horizontal and vertical models are different. So you cannot exaggerate the structures also. So structures should be to the vertical scale only, in single scale. That is what why I wanted to show in this one. So that the actual hydraulic phenomena near the structure can be assessed properly on the model. Okay, thank you. Do you have any questions? रिवर बेड का जो है सैंड का, ये जो है हाँ पार्टिकल, वो जो मैं आपको बताया ना, ये जो फॉर्मूला इसमें लिखा था, ये इधर देखिए, ये मैनिंगसन से मेनली डिपेंड रहता है। जो रिवर बेड का जो है ना, मतलब मैनिंगसन वैल्यू, तो रफनेस मॉडल का प्रोटोटाइप का सेम होना चाहिए, राइट? वो क्राइटेरिया मेन है। सो वो जब एन एम इज इक्वल टू एन पी, प्रोटोटाइप इधर अभी आप ये करेंगे NR इज इक्वल टू YR टू द पावर ऑफ 1/6 NR मीन्स रेशियो NR इज इक्वल टू क्या आता है NR इज इक्वल टू NM by NP इज इक्वल टू क्या आया है वो YR टू द पावर ऑफ 1/6 है ना YR to the power of 1/6. So when NM is equal to NP into YR to the power of 1/6. तो NM कैसा आ जाएगा इसका आप मल्टीप्लाई किया तो बहुत कम आ जाए मतलब मॉडल का जो है ना बहुत कम रफनेस आ जाएगा। तो जब कम रफनेस आ जाएगा तो आपका मटेरियल साइज कितना आ जाएगा बहुत छोटा। लेकिन मॉडल में आपको अवेलेबल मटेरियल क्या है 0.25 0.23 mm है D50 अल्टीमेटली D50 ऐसा तो ग्रेडेशन बहुत रहता है नीचे से लेकर ऊपर तक। तो जब हम लोग लेते हैं D50 लेते हैं क्योंकि सब मिक्सचर ऑफ ग्रेडेशन। सो D50 अभी आपका प्रोटोटाइप का कितना आता है 0.23 0.24। तो मॉडल में वही यूज करना है इन केस सिमिलरिटी होना चाहिए। लेकिन अल्टीमेटली क्या ट्रैक्टिव फोर्स कम्स इनटू पिक्चर है ना। ट्रैक्टिव फोर्स मतलब एग्जर्ट करना है जो है टाउ गामा RS है ना ये ट्रैक्टिव फोर्स इतना चाहिए। इसका जो 1000 ये केजी में बोल रहा हूँ ये बाई पी जो है ना आपका जो पर्टिकुलर प्रोटोटाइप का और मॉडल का ये करना है। यस आपको मालूम है स्लोप तो आपको ये ट्रैक्टिव फोर्स आ जाएगा इसको तो सम पॉइंट से 0.18 kg पर मीटर स्क्वायर आता है जनरली। ये अभी आपका जो है ना पॉइंट ये जो ट्रैक्टिव फोर्स लगता है पर्टिकुलर इसका सपोज से मेरा 500/70 का स्केल है उसको जो ट्रैक्टिव फोर्स 1.18 kg पर से। तो आपका जो शील्ड्स जो डायग्राम है ना ये में दिखा है ये जो है ऐसा स्पून कर्व बोलते हैं हम लोग। इसमें इधर D50 है और इधर टो है ट्रैक्टिव फोर्स। तो इसका जब भी 1.15 पॉइंट सपोज 18 आया है उसका D50 कितना आता है 0.25 mm जब आता है तो 0.25 mm आपको इजीली अवेलेबल है। तो इसके लिए वो ये इसमें क्या होता है ये जो मटेरियल सब ऊपर रहता है ये जो ये 0.25 में इट मीन्स वो जो मूवमेंट उसमें एग्जर्ट कर सकता है पर्टिकुलर स्केल को। ऐसा आपको हर एक स्केल का करना पड़ेगा। तो इनकेस नहीं हो गया सपोज आपका पास बेड मटेरियल है 0.25 या 0.25 mm देन व्हाट यू शुड डू रिवर्स इंजीनियरिंग बोलते हैं ना। इसको ये करके मेरा पास 0.25 है इसका ट्रैक्टिव फोर्स इतना है वो मैं कैसे डिजाइन करना है। इसलिए बोलता है ये जो स्केल जो हम लोग करते हैं ना इट शुड नॉट बी गो यू शुड नॉट गो इन वन गो। ऐसा ही हाव है मेरे पास सब डिस्चार्ज आता है बाकी इसमें होता है रिजिड बेड में आपका कुछ नहीं क्योंकि एकदम स्मूथ करने के बाद आपका वाटर लेवल मिला नहीं कम आया इट मीन्स दैट आपका मैनिंगसन बहुत कम है। तो फिर आपको उसको थोड़ा घिसना है जो इसमें से ना रफ पेपर सेंड। तो ऐसा करके आप फिर उसको बढ़ा सकता है। इनिशियली आप स्मूथ करके उसके बाद धीरे धीरे बढ़ा नहीं तो आपको मिल जाता है। लेकिन मॉडल में ऐसा नहीं इतना क्वांटिटी आप फुल निकालना पड़ेगा बाद में। इससे अच्छा स्टार्टिंग स्टेज में डिजाइन स्टेज में आपका पास मटेरियल जो है उसका पर्टिकुलरली इसका कौन सा स्केल सूटेबल है रिवर्स कैलकुलेशन करना पड़ता है। जनरली वो जो 0.25 आपका जो सिल्ट है हमारा मॉडल में जो सिल्ट है ऑलमोस्ट 0.23 से 0.25 का आसपास है ज्यादातर 0.3 हो सकता है कभी कभी। तो उसका जो मिलता है एबंडेंट मिलता है उसका हिसाब से हम लोग इसको जो ट्रैक्टिव फोर्स आपको मिलता है ना उसको रिवर्स कैलकुलेशन करना है। रिवर्स कैलकुलेशन करके आप फिर कहाँ तो ये जो स्केल में कहाँ तो बैठेगा आपका तो वो जो स्केल और देखना है वापस उतना स्पेस अवेलेबल है क्या उतना डिस्चार्ज अवेलेबल नहीं। तो ऐसे इटरेशन जो बोलता है ना तो हर एक इसका डिफरेंट स्केल करिए करके पर्टिकुलर स्केल में आप डिसाइड चूज करना है। जनरली वही इसके लिए बोलते हैं जो ट्रैक्टिव ये जो स्केल है ना डिस्टॉर्शन 5 का बेस्ट है 3 to 7 तक आपको कौन सा भी डिस्टॉर्शन से करता है। उसके बाद है तो फिर आपको ठीक से रिप्रोड्यूशन नहीं होगा स्केल इफेक्ट्स बढ़ेगा आपका जो है ये ऐसा है। और कुछ एनी क्वेश्चन? आज दोपहर को आप जाएंगे ना, उधर भी चाहे तो कुछ रहेगा तो साहब भी रहेगा, बताएंगे, हम लोग सब रहेंगे, आपको जो भी रहे इसका हिसाब से आपको कुछ आइडिया नहीं होगा, अंडरस्टैंड नहीं होगा, हम लोग उधर आपको एक्सप्लेन कर सकते हैं दोपहर, क्योंकि इसलिए आज रखा था सो दैट यू विल गेट बेटर आइडिया इन द आफ्टरनून, मॉडल में कैसा होता है, क्या फिनोमेनन होता है, जो बोला है कैसा करना है, ये ऑल दिस थिंग्स यू कैन good things. So I think there is no more question. If you have any question, please ask. There is no issue. Okay, I feel that everybody, I think everybody has understood properly, or nothing was understood. Two days maybe there, I don't know. But anyway, I hope everybody has understood the things. And of course, one go you may not pick up the things. So we may be giving this one for your this one understanding. You can just go to this one, and a lot of books are there. You can refer that also, and you can take it into your mind later also. There is no issue. Thank you very much for patience here. Thank you.